So, hi everyone, I'm Josh Moller-Mara. I'm working again on uncertainty, herding, and information cascades in the brain. Generally what this involves is what's called social learning, and I'll explain what that is right now. So, what is social learning and why is it important? We tend to make social decisions every day where we depend on the information of others to inform our own actions. This happens generally because we rarely have all the information we need to make an informed decision. Each individual has bits and pieces of information, but by looking at the decisions of others, we can infer their motivations to inform our decisions. So I'll give you some examples of kind of some social learning situations. So like knowing how to vote on an issue. Maybe you don't know exactly how, like everything about an issue, but if you look at kind of the way your friends vote, how your friends vote, you might infer that, some issue, you might sway one way or the other towards like an issue or something like that. Another funny issue is like claqueurs, which are basically these people. There used to be like hired professional people to applaud in like people that are just like hired to applaud in order to get other people to applaud. And you can see my professional claqueur here. Okay, that didn't work. But yeah, so people influence each other. Claqueurs were paid to basically just applaud. So, social thing. Herding, example. If everyone starts running for no reason, you're probably going to start running. And this is kind of, it makes sense that you should do that. That's kind of a rational thing. Or if you're an ant looking for food, you depend on the pheromone trails of others. Okay, none of you are ants, so if you're a human looking for food, you depend on the decisions of others, usually. Like when you're looking for, let's say, like a restaurant, you usually see how other people like act, which restaurants they pick. So, completely hypothetical example. Say you're walking through Berkeley, and you find this like froyo brownie place, froyo brownie sandwich place. Yeah, and we'll just call it, I don't know, Dream, because their froyo brownie sandwiches are dreaming. And there's a huge line outside of it. So this is an example where like social learning might happen, where you might depend on other people to form your decision of whether or not to go to create a dream. So you have to make inferences about why these people went to Dream in the first place. Maybe the first person went because he actually likes their froyo brownie sandwiches. The second person maybe went because he thinks the first person likes the froyo brownie sandwiches, but has no actual froyo brownie experience himself with Dream, and so forth. So people make these decisions like you have to infer what people know about Dream. Yeah, and if there's enough people assume that it's good just because there are people there, and then more people want it. So, what are information cascades? This is kind of based on Anderson et al. 1997. Information cascades happen when your private information goes against the crowd, and you follow the crowd. This in turn leads others to follow the crowd, and this is normally rational. In many cases, it's better for you to follow the crowd than to go with your own private information in certain situations. Although sometimes it leads to everyone making the wrong decision, in which case it's called a reverse cascade. An example is with ant death spirals, where ants just follow each other in a circle until they starve to death. So if you ever like follow somebody for like 15 minutes and you realize you've been in the same place like for 15 minutes, you should probably leave, otherwise you're going to starve to death. So how do we test this in the lab? We use the urn guessing game, which is described in Anderson et al. 1997. Say that, for example, there are two urns, urn A and urn B. This is an extremely simple example. One urn is chosen at random. It's not revealed to you which urn has been chosen. Like I'm going to pick an urn, A or B, by heads or tails. Maybe it's urn A, maybe it's urn B, you don't know. However, you do get to see a draw from the urn. So in this case, I just picked an urn, and I picked a marble out of it, and I picked red. Which one does it have to be in this case? A, right. So this is kind of an urn guessing game, and here's where we put the social part into it. Is we have 5 players all guessing from the same urn. or 6 players guessing from an urn, and they get to see a marble. Only they get to see their own marble, but they also get to see what other people guessed. Not what they drew, but what they guessed. So once an urn is determined, players take turns seeing marble from the urn in sequence. Players only get to see their own marble draw and not the draws of others. So this guy gets to see his red marble, nobody else gets to see his red marble. Marbles are replaced. Each player publicly guesses which urn they think was used, using their information and the guesses of others. So this person guesses A, because you're red, and red's just more likely to have come from urn A. Second person gets a red marble, more likely to be A in this case. Third person sees a blue, what's the most reasonable urn in this case? What it should have been B, because only B has a blue marble. So third player guesses B, correctly. Fourth person sees a red, but gets to see everybody else's guess, A, B. Why would this third person change from A to B? Maybe it's because he saw the blue marble. So this fourth person has to make inferences based on previous decisions, and he made infer that third person saw blue, so he goes against, even though this is red, he decides to go with B. So this is kind of a rational thing to do. Fifth player doesn't make a rational decision. And in our game, people who correctly guess the urn are $20. You're nothing. So how do we reason in this case? So in this case, what's like the probability of urn A? So randomly pick somebody. Yeah, exactly. What you probably did in your head is you probably went through all the Bayes rule math in your head. And you went, probability of urn given A is probability, given the draw red is probability of draw red given urn A, times probability of urn A over probability of draw red. I'm just kidding. In this case, I probably just count the reds. But this is how you would optimally figure out probabilities in this case. Now, say you get to see another person's guess, not their draw. Oh, how do you reason about other people's guesses? So you get to see other people's guesses, but not their draw, and what they think the urn is. If you're the first person, you just go with whatever urn's more likely. In this case, you basically just go with whatever urn's more likely. With the second person, you kind of disregard the first person's draw because they may have made mistakes, so your information is more trustworthy than theirs. If you're the third person, it's like you've seen two people's draws, and in this case, let's say you've seen A, and you draw blue. It's actually more likely, even though urn B is more likely just given the blue, it's more likely for you to guess that it's urn A. So, fourth person more interesting, he has to guess what person, the third person, third, and so forth. So this is how we might represent it in terms of a Bayes net. In a naive case where we don't model statistical dependencies, this is where guesses are independent. The only thing they have in common is an urn. So how to actually reason in this case is using this kind of Bayes net where guesses are recursively dependent on previous guesses. And obviously by the expression on all your guys' faces, you immediately understand this, so I'm going to skip through that. So our setup was done with using Python. It was a game code in Python using Pygame. We had 18 to 13 people play simultaneously in this game where they got to see other people's guesses about some urns, and they inputted their own subjective probabilities and their own guesses. So it's the same urn guess again. There's response time, subjective probability is what they thought the probability of urn A or B was, and the guesses. So we do see that, just replicating Anderson and Holt, that people do employ a more efficient strategy than just using the private information. If they just use private guessing, they would have around 77%, but they have near 80% guessing strategy for and this shows kind of over rounds, people get better than just using their own private information. So out of 378 rounds, people went against their own information about 33 times. And this worked in their favor 78% of the time. So this is good because if you just went with your own private draw, In these cases, you would have had a 30% success rate. So this is kind of the behavioral part of the task. What we're going to do next is to look at how people track these probabilities in the brain. So this is the behavioral part that I worked on this summer. The next part of this is seeing how people track probabilities, entropy, information gain in social situations. This is kind of interesting because it's kind of hard to pin down like neural substrates and social computation. I think social brain theory suggests that like intelligence kind of evolves to navigate social situations, so we don't see like one completely just social part of the brain, one thing that just does all the social computations. So lots of parts of the brains are used in making social computations. There's a lot of literature though for other kind of games. Cascades are nice in that they're slightly more realistic than other games. So what's next in terms of what I need to do for this project is to define parameters using social computation in Cascades game, estimate them based on the data that was run on like 18 people simultaneously, and to run control versus a treatment where people mentalize in a social situation versus a non-social situation in an error guessing game, and correlate probability updating in regions of the brain. And so I'd like to thank, that's basically it. I'd like to thank Ming, my mentor in PI, Ignacio Saez, one of the grad students in neuroeconomics lab, Tom Griffiths, who also helped me with the information cascades setup, and the efficient Big Carol and the service sponsors.